So, welcome everyone to our fourth session tonight. It's Learning with the Machines, Connected Data London's first online event for 2021, and which is all about graph-based data science and machine learning. And we have today with us Tara Safavi from the University of Michigan. Tara is a researcher who has been working on a number of things, including what's called CoDEx, a comprehensive knowledge graph completion benchmark. It sounds a bit cryptic at first, but I'm sure Tara will break it down for you. Tara, the floor is yours, and well, hope to enjoy your talk.
Thank you. So thanks everyone for coming to my talk today. As George already mentioned, my name is Tara. I'm a PhD candidate, soon to be PhD, hopefully, at the University of Michigan in Ann Arbor. And I'm doing research at the intersection of natural language processing and graph-based machine learning. So specifically, I'm really interested in ways that we can represent relational knowledge in machines and then use these representations for graph-based inference tasks. And actually, as of 2 days ago, if you're interested in the research side of things, we have a new preprint on neural and symbolic knowledge representations, which you can find on my website, which is linked right here. But today I'm going to be talking about my work in knowledge graph completion. Just a bit of background that I want to give before the talk is that this work that I'm going to present today is based off of a paper that was published recently at the EMNLP 2020 conference. So that's an NLP conference. If you search the title of this paper, CoDEx, a comprehensive knowledge graph completion benchmark, you'll find it freely available online. You can also find it on my website. So if you're interested in diving more into the research details, I would definitely encourage you to check out our paper. Okay, so I want to start by talking about how do we measure the quality of a knowledge graph. And I'm sure many of you are already familiar, but just in case you're not, a knowledge graph is a symbolic entity relation model of machine knowledge, usually world knowledge or some domain knowledge. So here I have a little toy example that shows some knowledge related to musicians. So one of the first things we ask about when it comes to knowledge graph quality is precision or accuracy. Basically, precision asks the question, out of all the facts that I have in my knowledge graph, how many of these facts are actually true? And because most modern successful knowledge graphs like ConceptNet, Wikidata, so on, have a human component, so they're either fully constructed by humans or at least verified by humans, they tend to be pretty high precision. On the other hand, we can also ask about recall, which is a complementary metric to precision. So whereas precision asks, out of all the facts I have, how many are true, recall asks, out of all the true facts in the entire space that I'm interested in capturing, how many does my KG have within it? So as you can imagine, recall is a lot harder to assess than precision because the space of facts can be very large. And moreover, we might not know how large it is in advance. However, in general, knowledge graphs are known to be incomplete. So there are some studies that have sampled parts of knowledge graphs like Wikidata or Yago and have just looked at, like, let's say, a small set of notable people and seen that many fields or relationships for those people were still missing. So knowledge graphs in general, they're growing always, but usually not complete. So then the question, of course, becomes how can we improve recall in knowledge graphs? And that gets into the whole field of knowledge graph construction and completion. So there are several different ways that we could do this. Actually, there's whole fields of research dedicated to this. One way is we can always hire more experts or crowd workers to augment our knowledge graph for us. And this is a pretty high precision, but kind of expensive approach. Another approach is that we can devise automated information extraction methods that identify entities and relations in documents. So this can be lower precision, but hopefully less expensive. And then a third way, which I'm going to focus on in this talk, is try using knowledge graph completion methods like link prediction. So all of these methods have their place in the knowledge graph construction pipeline, but I'm just going to focus on this third one. So when I say knowledge graph completion in this talk, or KGC, I'm basically going to be referring to the task of predicting missing edges, missing true edges in a knowledge graph. So here you see in this example, we have this little robot icon, and it's predicting a missing relationship in this knowledge graph related to the label of a released song. So knowledge graph completion can be seen as a supervised or self-supervised machine learning problem. So shallow or deep learning models can be developed and have been developed for knowledge graph completion. And the supervision setup usually works something like this. So first, let's say you have a model, you train it to predict missing entities or relations in a fraction of the triples in your knowledge graph under consideration. And then you will test the model in the same task, this prediction task, for the remaining triples that you held out. And there are also some other variants of this task, one of which I'll discuss later in my talk. So of course, I'm sure you're wondering, does this work? As we looked at in our paper, we have a review, and there's certainly a lot of papers that focus on this across AI conferences, machine learning conferences, NLP conferences. These are just some papers from the last 7 years that are fairly notable. But just because there are a lot of papers published doesn't really answer my question about does this work or not. So let's take a moment to rewind. It's really important to note, and I really want to emphasize in this talk, that all measured progress in AI research, when not being directly applied to a real-world application where we can, collect a set of metrics that are pretty direct, comes from benchmarks. So a benchmark can be seen as a data set that's supposed to accurately represent a real-world use case or a task. So in NLP research and ML research, benchmarks are used to compare competing systems, or more commonly just algorithms, for some task that the benchmark is supposed to represent, given a metric or a set of metrics. And theoretically, benchmarks let us say things like, model A is better than model B for task T on these certain metrics. So they let us basically compare models or algorithms. So of course, since we're talking about knowledge graph completion, then it's natural to wonder, what do benchmarks look like in knowledge graph completion research? If you'll recall from a few slides ago, we looked at a lot of papers in knowledge graph completion, and we investigated the benchmarks that they use in these papers. There are about 12 benchmarks, maybe 3 or so, which are the most represented in these papers. And we found a lot of problems with these benchmarks. One of the, I would say, the most prevalent issues is the reliance on very outdated data sources like Freebase. Another one, which has been noted in several papers before, is leakage between training and testing splits. And leakage just means that if you train a model on a certain split, then it's going to gather a lot of kind of easy information that makes testing too easy, essentially. So if you have leakage, then you're not really able to test the generalization capability of the model correctly. Some other things we noticed are a lack of standardized versions among different papers, low interpretability for humans, something I'll talk about later also. So in general, we found some problems. So as a result, then, we were motivated to propose a new data set, a new benchmark for the task of knowledge graph completion, which we call CoDEx, or a set of knowledge graph completion datasets extracted from Wikidata and Wikipedia. That's a lot to say, so for the rest of this talk, I'm just going to say CoDEx. And in the rest of this talk, I'm going to be answering a series of questions that you might have about CoDEx, or really any benchmark that someone proposes in research. So first of all, how was this benchmark designed and collected? What goals did you have? Second of all, what tasks can be tested on the benchmark? And what are some preliminary results? And then third, how does this benchmark compare to ones that were already existing in the literature? And what value does your new benchmark specifically add that you couldn't get from something else that already existed? So before I go on, I just want to mention that everything that we did, all the data, all of the models we ran, the code to run the models, is publicly accessible. And this QR code that you're going to see in the corner of every slide will take you directly to our GitHub repo, We have pretty extensive documentation on how to set up and use CoDex, and also open to issues and PRs if you have ideas about how to make it more accessible. Okay, so first question in our roadmap is, how is CoDex designed and collected? We seeded CoDex with the collaborative Wikidata knowledge base, which you might already be familiar with. It's a sister project of Wikipedia, and we think it's great, and I think the research community thinks it's great for a variety of reasons. So one, it's publicly available. It's quite large, so it's like a treasure trove of data, really. It's pretty high precision. It covers a lot of languages, and it's also linked very directly to Wikipedia, and I'll talk more about how these things are used in CoDex. So to get our initial seed data from Wikidata, we manually defined a set of world knowledge topics that we were interested in, these topics here. And then we collected Wikidata entity and relation types related to each topic and queried Wikidata for all the triples that satisfied these entity and relation types. So that got us around maybe 1.2 million triples in total to start with. And then from there, we filtered down these triples into smaller connected cores in 3 sizes, which we call CoDex S, M, and L to reflect their relative sizes. So each size has a different, we see each size as having a different use case. So CoDex S, the smallest, we see it more for testing of models or running computationally expensive approaches, let's say like rule-based learning. And then CoDex M and L were designed in terms of size to match existing benchmarks that are very commonly used in the knowledge graph embedding literature. So I'll talk more about a comparison of CoDex M to an existing benchmark later. So we see these as more general purpose and pretty much plug and play for knowledge graph embedding models. Okay, so as I said earlier, Wikidata and Wikipedia are tightly linked because they're sister projects. So they're both essentially stores of world knowledge. Wikidata stores knowledge in relational form as a knowledge graph. And then Wikipedia stores knowledge in document form with sort of semi-structured documents. So we use this linkage to our advantage in CoDex. For each entity in all of the CoDex datasets, we collected a snippet of text, which was the first paragraph of the entity's Wikipedia page. And we did this in 6 languages that are fairly well covered in Wikidata and Wikipedia, spanning a variety of scripts and language families. And this is fairly unique because existing KGC benchmarks either only have text in English, or more commonly, they actually don't contain any text at all. But our hypothesis is that, well, you know, with the advent of NLP, it's really useful to do graph-based machine learning with some side information, which is text. And then we also did something else kind of unique with CoDex. So let me give you a bit of background here. Most knowledge graphs, like this one I show in this figure, contain only true or positive knowledge. So that is to say, every fact that you see here, like Adele created hello, Beyonce is a citizen of the USA. All of these facts are true, right? But sometimes false or explicitly, let's say negative knowledge can be very useful because it can tell us what not to believe or maybe what not to do. So for example, if we had both positive and negative triples, knowledge graph triples, we could train a machine learning model to directly classify them, which you could imagine could be useful for things like misinformation detection on the web. But then the question is, if we only have positive data, how can we construct negatives in the first place? Where do these negatives come from? So briefly, what we did to create negatives for CoDex is we started with true triples like this one here. And then we corrupted the tail entities in each triple with another entity of the same type as predicted by a machine learning model to create something that looked plausible but was not necessarily correct. So here you can see we replaced the entity smooth operator with another entity, another pop song, Billie Jean. But this is a triple that's not currently in the knowledge graph. And then we manually verified these to make sure these were actually negatives. And here are some examples of actual negatives in CoDex with explanations. So for example, The first one says that Chopin was a conductor. So Chopin was a pretty well-known pianist, and he wrote a lot of music, but he didn't conduct any orchestras. So this is a triple that kind of, it's a hard negative, essentially. It looks true, but it's actually false. So later in this talk, when I talk about benchmarking, we're going to return to these negatives and show how they can be used for classification. Okay, so before I go on to the next part of this talk, I want to mention that in the GitHub repo, which is in this QR code, we have an interactive Jupyter notebook that you can run locally. If you have Jupyter, you can run it on a remote server. You can also run it in Google Colab. And this notebook is called Explore CoDEx, and it will basically show different stats of CoDEx. It will give some examples of content and also has a lot of nice plots in it. So if you want to play around with the data more, it's a really good place to start. Okay, so next question in the roadmap, what KGC tasks can I test on CoDEx? So in our work, we focused on 2 tasks, the first of which was link prediction. And this is by far the most common task in the KGC literature. And link prediction is essentially a ranking problem. Given a set of, let's say, test triples from a knowledge graph, you hold out either the head or the tail entities in these triples, and then you have your machine learning model rank the possible entities that like fill in the blank or answer the query for each query. So then we just compute ranking metrics like mean reciprocal rank and hit set K for this task. And then the other task that we did is triple classification, and this is less common in the literature, much, much less common due to the lack of real negative examples. However, since I talked about earlier, we actually have real negative examples in CoDEx. Classification is possible with our data set. And here, basically, you just feed a model triples, and you just have it label them as true or false, and you compute binary classification metrics like accuracy. As far as models and implementation, we provided baseline results for 5 diverse knowledge graph embedding models that were proposed within the last 10 years. We chose these models pretty carefully for a variety of reasons. 1, because they're all very well known, highly cited, and 2, because they represent essentially different classes of architectures, which kind of allowed us to like use each as a representative of its architectural class. So linear, nonlinear, shallow, deep, tensor decomposition, matrix decomposition, additive, so on. So in terms of the libraries that we used, we relied a lot on the libkge library, which is an open source knowledge graph embedding library that I will advocate for very heavily in general, because it provides really good functionality not only for implementing models and testing them, but for fairly comparing them and exhaustively tuning them in terms of hyperparameters. It uses PyTorch and this adaptive experimentation platform from Facebook. And basically, it makes it really easy to run a lot of different hyperparameter configurations for a model and like checkpoint the results, organize the results, and so on. And I think this is really important, and many people in the ML community think it's important, because there's a lot of recent work showing that when you properly compare older, maybe simpler models with newer, more complex ones, and you really exhaustively tune them, a lot of performance differences on benchmarks will disappear, which is to say that we as a community aren't always doing a good job of comparing models fairly. We're often biasing towards newer, more complex things. So libkge gives us a really good way to fairly compare our models. Okay, so let's look at some results. You're going to see a lot of numbers. There's going to be 3 metrics per model and data set, but I would say don't focus on the numbers themselves. We're just going to really focus on the takeaways. So the takeaways for link prediction is that we found for 2 out of the 3 data sets, actually, an earlier model, which relies on matrix factorization essentially, performs best when all the models were fairly compared. And then for the largest data set, CoDEx L, a more recent model, which relies on tensor factorization, performed best. And these are all shallow models. The only deep model that we considered, it was competitive, but never performed the best, which led us to wonder, is deeper really better in the case of link prediction? And I think this question is still kind of up for debate. We also found that depending on the input hyperparameter configuration that you gave to each model, performance varied hugely, as you can see by this plot. And this has been observed several times in literature before. So again, this goes back to what I was saying earlier, that it's really important to fairly and properly tune your models to get the best performance out of them. And also to report actually like means and variances and things of performance. Same thing for triple classification. We'll just, there's going to be a bunch of numbers, but we'll just talk about the takeaways. And here, we compared classification on positives and the hard negatives that we came up with in CoDEx to negatives that were just generated at random. That's kind of what tends to be done in the literature these days when triple classification is considered. And here, the main takeaway is just that when you generate negatives at random, all of these KG embedding models can basically perfectly classify positives and negatives. But when you give them hard negatives, negatives that look true but are really false, then accuracy drops a lot, up to like between 10 and 19 points. So this just is to say there's a lot of room for improvement. Okay, finally, the last question in the roadmap, which I'll go through briefly, which is just how does CoDEx compare to existing knowledge graph completion benchmarks and what value does it add? So for this, we compared to a very popular benchmark in the literature that's based off of Freebase. It's called FB15K237, it's hard to say. And we're going to focus on CoDEx M here for comparison because they're pretty much exactly the same size. So first, we did a brief qualitative comparison. We're going to plot the most frequent relations in each data set and just kind of inspect what do we see here. I just want to point out, though, that this plot and several similar frequency plots can be found in our Explore CoDEx Jupyter notebook that I mentioned earlier. So if you want to see some other types of like frequency comparisons, just head over there. So there's a lot here, but again, just two takeaways to consider. The first is that the Freebase data sets that tend to be used in the literature right now are very focused on a kind of narrow subset of world knowledge, which is mostly related to awards and entertainment, so like films and music. CoDEx, we actually tried to make it more diverse in terms of content, so you'll see that we do have films and music, but we also have politics, we have writing, things like that. The other thing is that for CoDEx, you can see the relation labels are pretty easy to read. They're just a couple words. But the Freebase ones are very lengthy. They're hierarchical in some way. Also, the documentation for Freebase has been deprecated because Freebase isn't maintained anymore. So we would make the claim that CoDEx, because it's based on Wikidata, is a lot easier to interpret. Okay, and then we also did a quantitative comparison of these two data sets. And what we did here is we devised a very simple link prediction baseline that we ran on each data set. Our simple baseline basically just computes some entity frequency statistics in each data set, and then it makes predictions solely based on frequency. And then what we did is we compared our baseline to the best knowledge graph embedding model on each data set, and then we computed how much does the model improve over the simple baseline. And the hypothesis here is that if the baseline performs better on a specific data set, then that data set is easier to model because you just really need frequency statistics in order to model it well. And then the fancy knowledge graph embedding isn't really as necessary. So what you're going to see in this plot here, you have an X and a Y axis. This is a cumulative distribution plot, and you can basically read as the learned knowledge graph embedding, the KGC model, improves up to X points, so that's the X-axis, over our simple baseline for Y% of the test set. So in practice, what we found is that our baseline actually outperformed the knowledge graph embedding for around 10% of the Freebase data set. And our baseline was within 5 points of the knowledge graph embedding for around 40%, so almost half of the data set. Our baseline was fairly comparable to the knowledge graph embedding, whereas for CoDEx, we didn't find that. And why is this? Basically, we found that the Freebase dataset has some very, very high degree entities in the graph that it's extremely skewed toward, for example, the entity that represents the United States. So because of this bias, it's very easy to make accurate predictions using entity frequency alone. You can just predict United States as the answer to a lot of queries and get like pretty decent accuracy. By contrast, we actually designed CoDEx to cover a wider variety of topics so that it wasn't skewed in this way. So the takeaway here is just that because of the way CoDEx was designed, it has less bias and therefore is not so easy to model with just entity frequency statistics. Okay, so that's it for my talk. Just to recap, if you remember anything from this talk, it's that 1, we introduced and motivated and described CoDEx. 2, I talked about what tasks can be benchmarked on CoDEx and gave some preliminary results, which the community can hopefully build off of. And then 3, I showed the value that CoDEx brings to the literature by comparing it to basically the most popular existing knowledge graph completion benchmark. So thank you so much for coming to my talk. I'm always happy to hear from people or to be connected with on social media. You can also check out my website if you're more interested in the type of research that I'm doing. And of course, definitely check out our GitHub if you want to play around with CoDEx more.
Great. Thank you very much, Tara. That was a really good talk, and I really liked how you made it approachable, basically, because it's quite deep, actually, academic research, and so it's great that you, at least for me, I was able to follow that. So there's a couple of questions. One actually is for me, and it has to do with the hard negative issue that you mentioned. And I was wondering, well, it's a 2-part question. So, if you could give an example of, like, a real world case where you would possibly encounter that, and what problem that would cause. I mean, you already mentioned that the accuracy drops in that case, but if you bring an example of what the repercussions would be, and if you have any insights as to how you can improve recall in that case.
Okay, so if I understood correctly, the question is about applications related to classification.
I was more specifically referring to the issue you mentioned around hard negatives. So when you have those in the evaluations that you did, you found that the recall drops quite significantly. You said somewhere between 10 or to 19 units, right? So I was wondering if you have any, if you have like any real world example where this happens, and if you have any insights on what you can do to, to mitigate that.
Yeah, so I think one real world example of where you might encounter hard negatives is, so if you think about methods that extract information from text. So I mentioned at the beginning of the talk, one way to construct a knowledge graph is to run a model that will essentially identify entities and relations and map relations to a vocabulary. And so they're not always correct, right? Like it might find something in the, like a information extraction model might find something in a document that looks kind of correct, and it outputs it as a triple to add to your knowledge graph, but maybe the confidence is not necessarily high. So it might be something like the example I showed earlier, where it incorrectly outputs a triple that, let's say, Sade wrote the song Billie Jean, which is not true. So you might at the end want to have another classification layer on top of that that essentially outputs a more calibrated confidence of, like, is this triple true or false? And in order to properly have train such a model, you need examples of good negatives so that it knows essentially, it's able to accurately classify these things. Does that kind of answer your question?
Mm-hmm. Yep, it does. Thank you. And there's another one from Ben, which is kind of related. So he's asking, if I interpret his question correctly, he's asking if you know of any use cases where CoDEx has been used, in whether that's research or industry, I guess.
Yeah, so CoDEx is basically intended to be a research benchmark, which is to say, it comes from Wikidata, right? So all of the knowledge that's within it is something that's already within Wikidata. It's not being actively used to augment Wikidata, but rather to test machine learning models and compare them. But the problem of link prediction or knowledge graph completion in general is one that I've encountered a decent amount in industry, and there's still like there's a lot of uncertainty about like whether knowledge graph completion models can be used in those cases. And part of the reason is that the benchmarks that exist in the research community aren't good enough. So for example, I have done some internships in the past where there were domain-specific knowledge graphs, for example, in finance or in, let's say, personal information settings, where graphs were being built to connect people's entities and relations that were mostly extracted from text. And there was like a strong need and desire to use automated methods to expand these knowledge graphs because they were always incomplete. But essentially the results, it was hard to tell whether existing models would really work on them. So CoDEx is supposed to help us better understand whether existing models, newly proposed models, can be used for that task. So basically bridge a little bit better what's going on in the research community, where there's always progress, but on these kind of like artificial benchmarks, and what's going on in the real world, which is there are some serious problems that people want to solve, and they want to use like innovative methods for them, but they're not exactly sure if they'll work or not.
Mm-hmm. Okay. And there's actually clarification on the question again from Ben. So he's saying that, let's say we have a real world issue where we're not sure which, he's saying that you have a property graph, and you don't actually know whether one version is good or another one. And he also states that you have a huge number of nodes, like a few millions, for example. So he's asking, if I interpret the question correctly, so he's asking, how would you differentiate between one version of the graph versus another one?
That's an interesting question. I think that that might not be exactly within the domain of CoDEx itself, but I can definitely talk a bit more about knowledge graph quality. So I would say that the best way to like verify whether you have a decent quality knowledge graph is to do some sampling and human annotation, because when it comes to knowledge, humans are usually the experts. So that's probably the way I would start. I'm not sure if that is like exactly related to the earlier question about real world use cases. Yeah.
Okay, great, thanks. I think for the moment we have no other questions. I'll just give like a minute or two to see if another one comes in.
Sure, I'm also happy to talk more in the community hour. Yeah.
Okay, cool. So, right, let's all head up to the community hour then. Thanks again, Tara, for a really nice talk, and we'll see you in a couple of minutes in the community hour.